definition of periodic motion. We are going to start with this. Yeah, short definition is repeated motion. If an object repeats its motion in equal time interval, back and forth, or in a circular path, this motion is called periodic motion. Earth's motion around the sun is periodic motion because Earth completes one revolution in 365 days. And after each 365 days, so Earth comes to the same position around the sun. That's why motion of the Earth around the sun is a periodic motion. Circular. All types of circular motions are periodic motion. But objects are not always moving on a circular path when they repeat their motion. They can also move along a straight line, over a curve, like these examples, like trapeze acrobat, they are swinging on a curve, or pendulum of a clock, or swing on a child on a playground swing. All these are periodic motions. To understand these periodic motions characteristic, we are going to study a simplest types of periodic motion, which is the motion of an object attached to a spring. So motion of an object attached to a spring is also a periodic motion. As you see, this mass is vibrating back and forth and equal time intervals. So this vibration is a periodic motion. And how this vibration happens, we have to first stretch or compress a spring to start the vibration. Yani, an object attached to a compressed spring, or first you can stretch it, and as connected to a stretched spring starts to vibrate around its unstretched position. So if we want to understand the characteristic of this vibration, first we have to study what is a spring, how spring makes this vibration. So we should first understand this. So first we are going to learn what is a spring, how we define it, how spring does this. So when we stretch a spring or pull a spring with some force, we know that this spring is going to be stretched. If you increase the force, the stretching will increase. Even if you double the force, stretching will double. If you triple the force, stretching will triple. If you increase it by 4, stretching increase by 4. When we divide force divided by stretching, the ratio, F over X, we are going to calculate a constant number for any spring. This constant number is called as spring constant. Yani, if you apply a force on a spring and pull it, and divide how much it is stretched, or if you compress a spring and then by some force and how much is compressed, if you divide F by X, you are going to calculate a number which is called spring constant, K. This spring constant, yes, it's calculated by F over X. How much force you applied, F applied, divided by how much the spring is stretched or how much the spring is compressed, which is K. And it's really according to the equation. You can get it because force is Newton. How much you compress or stretch spring, it is the distance, it's a length. A sine unit of the length is meter, so we are going to divide Newton by meter. It's going to be the unit of spring constant. And this spring constant K measures how stiff or how hard or how soft a spring is. If this number is a small number, it's a soft spring. If this number is a big number, it's a hard, tough spring. And every spring has its own spring constant. Yeah, spring constant does not depend on force. Our teacher, we calculate it by force. Yes, we do. But not only by force. We calculate spring constant by force divided by X. And it depends on not only force, also depends on how much it is stretched. That's why when force increases, X also increases. Why? Because K will stay constant for a spring. For every spring has its own spring constant, it's a constant number. For example, in this diagram, this picture, you see some springs seems to be soft, some seems to be tough. For example, this one seems to be soft, soft one. Most probably, spring constant is going to be a small number, like give it a random number, 10 Newton meter. But this spring, that spring, those seems to be hard springs. So their spring constant is going to be a big number, like, for example, 100. 150, 200, 200 something. So every spring will have a specific spring constant. This number will not change for that spring. So spring constant was measures how tough or how soft a spring is. If it's a small number, it's a soft spring. If it's a big number, it's a tough spring, hard to stretch. Yani, a greater value of the K means it's a stiffer spring. It's not easy to stretch. But a small number of K means it's a soft spring. It's easy to stretch. A greater force must be applied to stretch or compress a stiffer spring. Greater K needs a greater force. Smaller K needs a smaller force to stretch or compress them by the same amount. Okay, then there was an question about this. I mean, this is a ministry question. Quickly, I will solve it, and then how we solve it. See that? If a mass of 0.55 kilogram attached to a vertical spring and stretches the spring 2 centimeters from its original equilibrium position. Equilibrium position, you know what it is, unstretched position. What is the spring constant it says? So now let me draw the case. There is a spring. This spring is initially unstretched, like this. After that, we are going to attach a mass to this spring. Of course, after attaching the mass, this spring will be stretched. So after that, we are going to attach a mass. After the mass is attached, this mass is given as 0.55 kilogram. M is equal to 0.55 kilogram. This spring will be stretched. Why is it stretched? Because this mass applies a force on the spring, which is equal to gravitational force, yani Ft. Acting on this mass causes this spring to be stretched. How much is Ft? M times G. M is given 0.55. So G is 9.81. When we multiply them, we will get it as, I think 5.4 was the answer. Yes. 5.4 Newton was applied force. When we apply some force, it's going to be stretched or compressed. How much to stretch in this question is given? This stretching is 2 centimeters. Yani, this spring stretch X is equal to 2 centimeters. Of course, we should use meter in calculation, 0.02 meter. After the calculate the spring constant, we know that K is equal to the force applied on the spring to stretch it, which is Fg in here. Yani F applied, let me write the equation first, applied force divided by how much this applied force stretch the spring, which is X, will give us how much is this spring constant. So applied force was 5.4, which was the gravitational force, was the applied force in here, divided by 0.02. Result is going to be, I think, 270 Newton divided by meter. Be careful in here. To stretch a spring, you have to apply some force first. Yani, the equation which we write, not about the restoring force. It was the force which you pulled the spring. Okay, then let's go continue the remaining part. Still, we didn't start the system to vibrate. What did we do? Only we stretch a spring by applying some force. As if applied stretches the spring, we are going to observe that when I was pulling this mass to the right, I am going to feel that this spring is pulling this object back towards this unstretched position. So, the spring pulls this mass back by exerting an oppositely directed force named as elastic force or spring force. It's so natural. Why spring force? Because they applied by a spring. Why is it elastic force? Because spring is an elastic object. So this elastic force or spring force is always in the opposite direction of displacement of the mass. Look at the displacement of the mass. When I was talking about displacement, we are comparing its new position with respect to the unstretched position. Yani, reference point is going to be unstretched position. From this position where the mass is, in here. In which direction is the displacement? Positive x direction. Look at this elastic force or spring force. In which direction? Negative x direction. So this elastic force, or other name is spring force, always in the opposite direction of displacement of the mass. then in which direction mass displays, force is going to be opposite in direction. So this elastic force, spring force, in the opposite direction of the mass displacement from the unstretched position. Second thing, when you pull it more and more as x increases, you are going to feel that this force, elastic force, also proportionally increases in magnitude. Yani they are directly proportional. Second property of this elastic force is it's directly proportional to displacement of the mass. So when we combine these two properties, I can write equation about this elastic force. First, elastic force in the opposite direction of the x. Yani, if x is in positive x direction, so elastic force must be in negative x direction. That's why there must be a negative sign in this equation. I'm going to write an equation. So, second thing, if I am going to write an equation, there must be a constant. Constant. Every proportionality is changed to an equality by a constant. This constant is spring constant. In fact, our equation is this. Yani, F is equal to F elastic is equal to K times negative x. Why negative x? Because as you see, these two vectors are opposite in direction. They are related by a negative sign if two vectors are opposite in direction. But mathematically, putting negative in here and in here has no difference. Yeah, we can take this negative from here and put in here, we can get equation for elastic force. Yani negative kx. This equation tells you that, yes, as x increases in magnitude, elastic force also increases in magnitude. Yani this one. And this negative sign says you that direction of x and direction of the elastic force always opposite in direction. This force, what will this force do? If I release this object, this force will take this object back to its original unstretched position. To take something as original, especially in history area, is called restoration. Yani this force always wants to take object back to its original unstretched position. That's why this force is also named as restoring force. This force always pushes or pulls the mass back towards original unstretched position. That's why these kinds of force, yani any force, which always wants to take a system back to its original unstretched or before making the vibration, whatever the position is, those forces are named as restoring forces. And this restoring force, then question ministry asked this way, which of the following is the restoring force for mass spring system? So elastic force is the restoring force for mass spring system. If I ask you a question like this, A, gravitational force, B, normal force, C, elastic force, D, none of them. So C, elastic force, is going to be the answer for restoring force for mass spring system, because this force always wants to take this system back to its original unstretched position. When it is stretched, it doesn't matter when it's compressed, also like this. To compress, I should push it to the left. Restoring force, this elastic force wants to take it to the again, where initially this system was. Okay. Then let's continue. If the spring is stretched by applying some force on the mass and then released, I am going to pull it, and after that, I will release it. What's going to happen? This system will start vibrating around this unstretched position under the influence of just one single force. Because when I remove it, applied force is 0, no more applied force. One force is left. What is that force? Elastic force is left. If I release it, this force is going to be removed. Only elastic force will be acting on this mass. And this elastic force will start this mass to vibrate between two extreme points, between here and here, around this unstretched position. This vibration is called simple harmonic motion. But simple harmonic motion is a special type of periodic motion. There are several periodic motions. If an object repeats its motion, we say it's periodic. Circular motion can be periodic, or on a curve it can be periodic. But this is a special type of periodic motion. Why special? Due to a restoring force. If a vibration is due to a restoring force, then we can name this vibration as simple harmonic motion. So due to restoring force, the mass starts vibrating back and forth around unstretched position. This periodic motion is named as simple harmonic motion. Here is the definition. Any periodic motion, yes, it's a repeated motion, that is result of a restoring force is described as simple harmonic motion. Then every simple harmonic motion is a periodic motion. It's a repeated motion. But can we say that every periodic motion is a simple harmonic motion? No. Circular motion. In there is just centripetal force. We don't have restoring force there. So then circular motion is not a simple harmonic motion. They make every simple harmonic motion is a periodic motion, but be careful, every periodic motion is not a simple harmonic motion.
Centripetal force, bu circular motion period
It's periodic motion. Yes, we know about it. Okay, one more thing. The position of the object when the spring is unstretched or uncompressed is called equilibrium position. Unstretched or uncompressed. Why is it so called? Because when x0, no stretching, no compression. Yani elastic force is zero. Yani net force acting on the object at that position is zero. If the net force acting on object is equal to zero, what equilibrium is it called? Translational equilibrium. Yani when the mass just at this position, right here, at this position, spring is neither compressed or nor stretched, is called as equilibrium position because net force acting on the mass is zero. Okay. Then, as the system is vibrating back and forth, of course, size of the spring is changing. Stretched, compressed. Stretched, compressed. We are making a change in the shape of the spring. As shape of an object is changing, especially if it is an elastic object, so we are going to observe there is a change in elastic potential energy. What is elastic potential energy? If a spring or elastic object, not only spring, it can be a rubber too. If an elastic object is stretched or compressed, this object will store energy called as elastic potential energy. Best example is spring. If the spring is stretched, we can calculate, you calculate in the 11th grade, elastic potential energy by an equation 1/2 kx squared. K is about spring constant, how tough the spring is. X, how much you stretch or compressed this spring. So, in this case, that if X increases, elastic potential energy increases. Yani if you stretch a spring more and more elastic potential energy is stored. If it is less stretched or compressed, less elastic potential energy is stored in this spring. No compression, no stretching, no elastic potential energy in the spring. The more the spring is stretched or compressed, the more elastic potential energy stored in the spring. Bow example is about this. Your book studies the bow example when it starts about this energy part. Just like a spring, bow is also an elastic object. Maybe you remember you didn't believe that bow is an elastic object. So when you pull the spring back, you are making a change in the shape of the bow. Look at the shape. This is initial shape 2. When you pull back the spring, shape changes to 1. Yeah, so is there a deformation? If there's a deformation, of course, there is going to be a change in the elastic potential energy. So when you pull the spring back, you store elastic potential energy in the bow by changing the shape of the bow. So the energy which changes the shape of the bow is stored in the bow as elastic potential energy. Then you are going to release the bow with this arrow. What's going to happen? So when you release it, the arrow will start moving away from the string with the great speed, which means elastic potential energy stored in the bow will be converted to kinetic energy of the arrow. But not only arrow is moving, also string is vibrating, also bow is little vibrating. That's why we say that original stored elastic potential energy is converted to kinetic energy of the bow, not only bow, arrow, and bowstring. This is, conservation of mechanical energy. If a system has potential energy can be elastic or can be gravitational potential energy. So while it's converted from one type to another without friction or air resistance, these two energies at the initial and final, they must be equal to each other. Initially we have just elastic potential energy in the ball. Finally we have kinetic energy in this arrow, ball and bowstring. So these two energy must be equal to other, known as conservation of mechanical energy. This conservation of mechanical energy holds constant for a vibrating mass spring system as well. Yani, when this mass is vibrating right and left, back and forth, just one quantity always constant. Total mechanical energy, which is the sum of kinetic energy and elastic potential energy. It stays unchanged. Of course, if there is no friction, if there is no air resistance, yani no damping. Remember, we will define it later, but now you know all of this. Only one quantity never changes as this mass is vibrating right and left. All other quantities, what are they? Elastic potential energy changes. Kinetic energy of the mass changes. Restoring force changes. Acceleration of the mass changes. Velocity of the mass changes. All of them changes as this system is vibrating. Even they are continuously changing. Yeah, it's not like this. It changes at some position, it doesn't change other position. No, they continuously change as this mass is vibrating back and forth, except one quantity, total mechanical energy. Talk about how these quantities will change. Yani, as this mass is vibrating right and left, how these quantities are changing. Just I'll talk on the table, not detailed part. Remember the table. As this mass is vibrating, it's vibrating two extreme points. One of them is maximum stretch. It's represented by positive x maximum. The other one is maximum compression, which is labeled as negative x maximum. At maximum stretch and maximum compression, which means object stops. If it is moving, you cannot say it's maximum stretch or compression. An object stops for an instant. If an object stops, what is velocity? Zero. At this maximum stretch or maximum compression, velocity is zero. Look at that. Velocity magnitude is zero at maximum compression, zero at maximum stretch. If velocity is zero, of course kinetic energy must be zero. Kinetic energy is zero at maximum stretch, kinetic energy is zero at maximum compression. But if kinetic energy is zero, system's energy completely must be elastic potential energy. So at this position, as you see, elastic potential energy at maximum stretching or maximum compression stretching is maximum. Look at that. Maximum and maximum. Do you remember that I said them? These two are same family. So they always change together. If one of them is zero, the other one is zero. If maximum, maximum, yes. But other three, same family. The elastic potential energy is maximum, as restoring force is maximum because x is maximum. Maximum compression, maximum stretch, x is maximum. Greater x means greater restoring force. Restoring force is maximum and acceleration and restoring force directly proportional maximum. Maximum stretch again, they are maximum. Yani first three maximum, next to zero. First three maximum, next to zero. Of course, the system is vibrating right and left. Finally, it passes through another important position, which is equilibrium position. What does equilibrium position mean? Net force acting on the object at that instant, at that moment is zero. Restoring force must be zero. If restoring force zero, acceleration must be, according to Newton's second law, zero. No compression, no stretching. So which means elastic potential is zero. If the first three, a family zero, other two, another family must be maximum, so the mass passes from equilibrium position with the greatest speed. Then, that's why kinetic energy is maximum, velocity is maximum. These are enough, in fact, for the perspective of the 12th grade of ministry. Then general questions are asked about maximum compression, maximum displacement, or maximum stretch, again maximum displacement, or equilibrium position. Okay? And as I said, for an ideal system, yani, what does ideal system mean? No energy lost because of the friction and air resistance. So, in ideal system, mechanical energy of the system keeps constant, so the mass systems will oscillate infinitely. But in a physical world, yeah, a real system, of course, friction exists. Of course, air resistance exists. What's going to happen? This mechanical energy will be converted to heat. That's why mechanical energy will decrease and system finally stop vibrating. This is called damping. Until now, any questions?
No.
All right. Then, pendulum. When you suspend an object from a fixed point and make it swing, it doesn't matter what it is. Suspend it from a point, make it swing. That system is called pendulum. Yani, it can be you also. Hang yourself from some place and start swinging. You're a pendulum. Yes, it's it. These are pendulums. Make them swing. Okay. In our book, they are starting the pendulums by trapeze acrobats. They are also swinging. There are ropes, so they are holding the ropes and then starting to make themselves swinging. It's a pendulum. But this pendulum is a physical pendulum. What does physical pendulum mean? So you cannot neglect the mass. You cannot neglect air resistance because area is not that small. There are two people, sometimes three, sometimes four. So you need a very thick rope to make them swinging because ropes are very thick. Their mass cannot be neglected. You should count about their vibration. Like they have a moment inertia, so they infect the motion. So swinging trapeze acrobat is a physical pendulum. Yani you cannot neglect the mass. You cannot neglect the air resistance. That's why all of them affects the vibration. It's called physical pendulum. Then question, vibration of this trapeze acrobat is absolutely periodic motion because it's repeated motion. Is it a simple harmonic motion? We are going to try to answer this question. But to answer this question, we have to choose a model because starting trapeze acrobat is not easy. There are many factors affecting the vibration as resistance and also because of the big mass, moment of inertia, rotational technology must be involved, so it makes things hard to study. That's why we are going to choose a model for this trapeze acrobat, which is the simple pendulum. Simple pendulum, I forget to bring it, but anyway, so you know what it is. So we are going to choose a simple pendulum as a model for swinging trapeze acrobat. If the vibration of this simple pendulum is simple harmonic, then I am going to say that vibration of trapeze acrobat can also be simple harmonic. But to name a vibration simple harmonic, we should check for restoring force. If there's a restoring force, then I will say that this vibration is simple harmonic. So first let's define what is a simple pendulum. As I said, simple pendulum is opposite of physical pendulum. Opposite of. Yeah, in physical pendulum you cannot neglect the mass of the rope, but in simple pendulum you will neglect. In physical pendulum, air resistance must be taken into account, but in here, because mass is so small, air resistance will be neglected. Simple pendulum is we only care about this mass vibration without thinking about air resistance, without thinking about rotational kinetic energy or other stuffs. Okay, so we are going to check for restoring force. If there's a restoring force in this vibrating simple pendulum, after that I am going to say that it's a simple harmonic motion. By the time, in vibrating mass spring system, we measured the vibration by the length of the mass from the equilibrium position. Now, maximum displacement on the left, then on the right, we measure this distance by centimeter or meter. But in pendulum, in simple pendulum, displacement of the pendulum's bob will be measured by an angle. We don't use distance, even though your book says distance also, but we don't. We are using angle. What angle this pendulum swings away from this equilibrium position, it's going to be displacement on the right or displacement on the left, theta. Then let's check it. if this vibration is simple harmonic or not, but we are going to search for restoring force. If we find it, yes, it is a simple harmonic. Okay. There are two forces acting on this pendulum's bound. One of them is gravitational force downward. The other one is tension force along the rope. Look at this tension force. Tension force is always perpendicular to the direction of motion. Any force perpendicular to the direction of force cannot be restoring force, because restoring force always acts in the opposite direction of the displacement. These forces cannot be restoring force. That's why I'm going to eliminate theta, say Ft, sorry, Ft always perpendicular to direction of the motion. One force is left, Fg is left. Now, I am going to study component Fg. One component is the y component, the other one is x component. Y component is also perpendicular direction of the motion. That's why these two cannot be restoring force. What is left? Ftx is left. Is it in the opposite direction of displacement? Is it in the opposite direction of displacement? Check it. This is displacement direction. It is a kind of counter clockwise. Look at Ftx. It pulls the mass in the opposite direction of the displacement. Yes, it is. It's in the opposite direction. One condition is provided for restoring force. Yani, restoring force must be always in the opposite direction of displacement. But we need one more component, one more condition. What was it? It must be directly proportional to displacement. What is displacement in here? Theta. As theta increases, Fgx must increase. As theta decreases, it must decrease. Let's check if it is like this or not. We are going to write Fgx. How can I calculate Fgx? I can calculate Fgx by using this triangle. This angle is theta, just like that. This is a right angle triangle, yes it is. This side is Fgx. This side and that side are equal to each other. And length of here and here are equal. In this right angle triangle, Fgx is opposite perpendicular leg of this angle. Hypotenuse Fg. To calculate opposite perpendicular leg, I have to multiply hypotenuse Fg by sine of this angle. Sine Fg sine theta is Fgx. So Fg sine theta is the restoring force if it is. As theta increases, Fgx is increasing or not? Yes, it is increasing. Even directly proportional increases, but at small angles. Until 15 degrees. If theta doubles, you are going to observe that Fgx also doubles. If theta triples, also triples. But this is only happening when the angle is relatively small. Yeah, less than 15 degrees. Then I can say that. Okay. This Fg sine theta is first in the opposite direction of displacement, correct. Directly proportional to theta until 15 degrees. So then I can say that until 15 degrees, this vibration is simple harmonic. But an angle greater than 15 degrees or 15, we don't count is as simple harmonic because theta and Fgx are not directly proportional. Kısaca ne diyorum, tekrar ediyorum, I shall shortly. According to this equation, first know that. What is restoring force for simple pendulum? First question. Fg sine theta. What is Fg? Weight. Fg sine theta, which component of the weight? The component which is tangent to the direction of the motion. Look at that. Fgx is tangent to this path. Tangent to this path. That's why in one listening question they ask this way. Which component of the Fg is restoring force? The component which is tangent to the direction of motion is the restoring force. The one which is perpendicular is not restoring force. We know that. Second thing, what is its equation? Another listening question. Fg sine theta. Another one. Third one. When, until what angle this vibration is simple harmonic? Less than 15 degrees is simple harmonic. Why is it so? Because until 15 degrees, theta, this theta and this Fgx directly proportional. Angle greater than that, it is not directly proportional. That's why it is only periodic. Yeah, if angle is greater than 15, vibration is only periodic, but not simple harmonic. But less than 15, periodic and also simple harmonic motion. Clear? And next one. gravitational potential energy of the pendulum's bob. As this pendulum is swinging, you see that its height from the lowest positions continuously change. Rising on the left, rising on the right. So height is changing. As height of an object is changing, what happens? Its gravitational potential energy is increasing. As it is swinging to the right, as it is swinging to the left, its gravitational potential energy is continuously changing. Then I am going to say that, yes, this system also has potential energy, but this potential energy is different than mass spring system. Mass spring system, potential energy was elastic potential energy, but now it is gravitational potential energy. But how they change are exactly the same. Elastic potential energy was maximum at maximum displacement. Gravitational potential energy is also maximum at maximum displacement. Elastic potential energy was zero at equilibrium position. Gravitational potential energy is zero at equilibrium position. Yani how elastic potential energy changes, gravitational potential energy changes the same way. That's why this table is the same for both mass spring system and also simple pendulum. Yani if you know about mass spring system, you know everything about simple pendulum too. Only difference, instead of elastic potential energy, what we want? Gravitational potential energy. All other quantities, the starting force, acceleration, kinetic potential energy, how mass spring system changes, in the same way, simple pendulums, these quantities are changing. What is unchanged? Mechanical energy. That is unchanged, which is the sum of the kinetic energy and potential energy. Of course, we should think system is undamped. Yani no damping. In this case, total mechanical energy will stay unchanged. This dark line, yani horizontal black line, represents total mechanical energy as pendulum is swinging between two maximum displacement, from negative theta maximum to positive theta maximum. This is unchanged. But what two energy is changing? Kinetic energy and potential energy. At maximum displacement, kinetic is zero, which is blue, but potential is maximum. Then potential decreases, but kinetic increases. At equilibrium position, kinetic is maximum, potential is zero because it's at the lowest position, but changes again oppositely. This blue is kinetic energy change, red is how potential energy change, but their sum always unchanged. This statement is last, this is missing question. So, the mechanical energy, yani the sum of the kinetic energy, potential energy and kinetic energy of a simple pendulum is conserved. Yani unchanged. Yani constant if the system is frictionless, no damping.